Welcome. This is functional analysis, second session on open mapping theorem. In the last session, what we proved was very interesting. We had a continuous linear map T from a Banach space X onto another Banach space Y. We proved that it's an open map if and only if the image of the open ball in X, Bx, that is TBX, contains an open ball B0R, that is an open ball in Y, that is B suffix Y 0R. We already proved it. Towards the end, we proved one thing. What we proved was we could not prove by0r is contained in b of x, but what we proved was there is an r positive, so that the open ball b0r in y is contained in tbx closure. Right now we are going to say that perhaps by shrinking r, let's say by r by 2, r by 3, we will actually show b0r by 2 or r by 3 is contained in tbx itself. Then we would have proved the open mapping theorem. That is the basic idea. Now let's look at the first thing. First part was the closure of tbx contains some by0r, and there what did we use? We used the completeness of y. In fact, we made it a lemma. We went through the proof. Toward the end, we formulated a lemma. What is the lemma? Let x be any Banach space. Let C be a subset of x. What are the properties? C is symmetric, C is closed, C is convex, and union of NC, that is scalar multiple n times C. That union, as n varies over Nachum, is all of x. If you have such a C, then we proved that there exists an open ball B0R in X, that is contained in C. B suffix X 0R is contained in C. Right? And for open mapping theorem, what was our C? The closure of TBX. That is, BX is the unit ball. Take TBX as the image and take its closure in Y. Then that C has all the four properties which we mentioned. Okay, there we proved. Therefore, we proved B0R is contained in the closure of TBX. Okay, just recall. This is how one should recall quickly what we have achieved, rather than going line by line and getting confused. Okay, once you have the goal in mind, then it will be easier for you to review. Okay, now we want to prove the next one. Okay, let us get started. I don't want to keep saying the same thing. So this time what I am going to do is something different. Okay, I can go through the second part of the proof, namely perhaps by0r by 2 or r by 3 is contained in the image tbx. I can prove that directly and then try to extract the lemma. Alright, that's what we did for the first part, right? This time I'm going to state the lemma first and see how to use it in the second part. Just for fun. Okay, so let us share the screen and start looking at the lemma. So what is the lemma we want to do? So let Y be a non-linear space, not necessarily complete. That is, need not be a Banach space. Okay, so what is our assumption? Let A be a subset of Y and let F equal to A closure, and assume that there is R positive, so that B0R is contained in F, that is A closure. Right? So what does that mean? Try to understand. Therefore, if Y belongs to B0R, that is contained in A closure. Remember, A closure is set of adherent points. Adherent points of A. Right? This I had already mentioned in the last lecture. So what is an adherent point? If X tau is a topological space, okay, A is a subset of X and X belongs to X, this is an adherent point of A if for every U in tau, so that X belongs to U implies U intersection A is not empty. This is our definition, right? Okay, therefore if since Y belongs to that, it's an adherent point of A, therefore there is an A1 such that, okay, norm of y minus a1 is less than r by 2. That is, you are looking at the open ball by r by 2, and this intersection a should be non-empty. Therefore, there is an a1 with this. Is that clear? Right now, where is my a1? Okay, is that clear? So I want to proceed by induction. Okay, so what I want to claim, let us, no, I will complete the proof later. Let me just, the statement I will later. Now where does this belong to? This belong to b0 r by 2, right? Now notice we had already gone through this logic in the first lecture. b0 r by 2, since b0 r is contained in f, b0 r by 2 is contained in half of f, but again we have seen this is nothing other than half of a closure. Okay, all these things seen in session 1. Okay, in some context or other I have proved all these things. I didn't expect you to accept it on faith. Okay, we had already proved that, right? Now we can do the same thing. Now since y minus a1 belong to b0 r by 2, okay, this is an adherent point of what? Half of a, right? That means there is an a2 in half of a, that is such that y minus a1 minus a2 is less than last r by 2, therefore it is r by 2 squared, which is 2 to the power minus 2 times r. Okay, here what I am looking at? I am looking at the open ball b minus a1 r by 2 squared. This intersection a should be non-empty. Therefore, there is a2. Okay, is that clear to you? So now I can proceed by induction. So what will I have? I will have a sequence an, so that where is my an? Remember, a1 was in a and a2 was in half of a, right? Look at that, a2 was in half of a, therefore my an should be in 1 by 2 to the power n minus 1a, that is 2 to the power minus n plus 1 times a, right? And with what property says that norm of y minus a1 plus a2 plus an should be, let us look at this, y minus a1 minus a2 should be less than r by 2 squared, therefore 2 to the power minus n. Yeah, right? So if I proceed like this, therefore what do I get? I get y equal to summation n equal to 1 to infinity, and what are my an's? An's are in 2 to the power minus n plus 1. Okay, now we proved the result. Let me formulate the statement. Okay, because unless I go through this, I may not have complete stated the thing properly unless my memory is good. Okay, so that let's go through that. There is an r, assume that. Okay, then statement now. Okay, continues. Okay, completing the statement of the theorem, statement of the lemma. What is that? There exists a sequence an, so that where does an lives? An lives in 2 to the power minus n plus 1 for all n, and my y is summation an 1 to infinity. For every y in a, there exists a sequence an, so that an belongs to this times a, 2 to the power minus n plus 1 times a, and y is the summation. Okay, please go through the statement, take some time, make sure we proved it. Okay, so pause, review, proceed. right? So now I want to apply the lemma. So let us go back to open mapping theorem. I usually call it OMT, it will be easier, right? What did it say? X and Y are Banach spaces. This is on to continuous and linear. That is what you call bounded linear operator mapping X, that is Tx equal to Y. Okay, then we want to prove T is open map. Okay, so we had already seen enough to show. Okay, there is a R positive, so that by0 R is contained in T of Bx. What was T of Bx? It's an open unit ball in X, and by0 R means open ball centered at 0 radius R in Y. Okay, and what did we prove? The first part, what we proved was this: there exists R positive, so that by0 R is contained in TBX closure. Yeah, this is all we have proved in the first session. Now come back and try to use the lemma. Now I can, therefore I can take my A to be equal to TBX, my F equal to TBX closure. Then what do I know is there exists by0R which is contained in F, right? Therefore what did I know? What I said was, for each, give me any Y in by0R, okay, there exists a sequence an in A, not A, in 2 to the power minus n plus 1 A, right, such that my Y is summation an. Okay, this by a lemma, by the last lemma. Okay, now let's look at what is an. An is 2 to the power minus n plus 1 A, but what is A? 2 to the power minus n plus 1 T of Bx, right? Again we have seen this is nothing other than by linearity etc. We had already seen this is 2 to the power minus n plus 1 Bx, right? Therefore an is in the image of this particular open ball. That means there exists an xn, that is there exists xn where in 2 to the power minus n plus 1 Bx, so that my an is T of xn. Is it okay? Therefore what do you think I have done? Therefore my Y, combine these two statements, this one and this one. Okay, now what is this combining this and this? Okay, what do I get? 1 and 2 imply my Y is summation Txn n equal to 1 to infinity, right? Now let's look at what do I know about xn's. Xn's are in 2 to the power minus n plus 1 Bx. Therefore norm of xn is less than equal, strictly less than 2 to the power minus n plus 1, right? From n of course run from 1 to infinity. Therefore let's look at this series xn in x 1 to infinity. Okay, this is norm conversion, that is this is absolutely conversion. Less than or equal to 2 or less than 2, actually less than 2, but if you want assume less than or equal to certainly less than 3. Is it okay? Therefore what do I know? Since now is the time for the second lemma, I did not use the fact x is complete. You understand? Therefore my Y equal to summation an is correct. There is no problem the way we got it, because the norm of Y minus the partial sum a1 a2 an, okay, within bracket, that's less than 2 to the power minus n. That shows the convergence. There was nothing to do with completeness of Y in the second lemma. But when I want to apply the second lemma in open mapping theorem, I have to assume, okay, my x is complete, because my an is happens to be Txn. Therefore I am looking at xn. Now since x is complete, okay, then you know any absolutely convergent, that is non-convergent series is convergent. This shows this is convergent. So let x is equal to the sum of the series. Do you follow that? So P or P. Therefore, therefore I have x equal to summation x and 1 to infinity. Norm of x is strictly less than 3 and my y is summation tx. Summation tx. But remember t is continuous plus linear, right? Therefore, what will be t of x? T of x will be t of x. Therefore, this is t of x, right? Therefore, what you have shown is there exists an x given for every y in by0r, which is contained in tbx closure if you want, sorry. Okay, there exists an x in 3 times bx, so that y is tx. That means, what does it mean? That means by0r is contained in 3 times tbx, that is t of 3bx, but this is same as 3 times tbx. Therefore, by0r by 3 is contained in tbx. Okay, notice that how I can pull out the scalars in set and closure of the set, etc. That is why in the first session I took lot of pain to prove it rigorously. Most often, you know, teachers will keep on writing, you tend to accept it on faith. Okay, very rarely you sit down and check. Many of the students don't do that. You may. Have you proved? So, what have we shown now? We have shown that the image of the open ball TBX contains an open ball centered at 0 in Y. Right? That is what we needed to prove for open mapping theorem. We have proved it. Therefore, the proof is complete. So pause, review, proceed. Okay. Now, closely related to that is what is called bounded inverse theorem. In the preliminary things to session 1, I talked about why open mapping theorems are very popular. Okay, if you have a map of required kind which is a bijection and open, then in some sense it induces an isomorphism. That's the intuition. Okay, I hope some of you try to spend some time what I said in the first 10-15 minutes of open mapping theorem. This is what I included. So this is going to prove that. So what we want to do is the following. That is, suppose x and y are Banach spaces, and suppose t from x to y is continuous, linear and a bijection. Okay. Now by open mapping theorem I know t is open. Right? Now you know if I have two topological spaces x and y and f is from x to y a continuous bijection. Okay. When do I say it's a homeomorphism? If f inverse from y to x is also continuous. But also there is an equivalent version, a map which is continuous and bijection which is open plus open implies f is a homeomorphism. Right? This is from topology. That is, a continuous bijection plus open map is a homeomorphism. Right? Therefore, I know that this map T from x to y is a homeomorphism. Right? Therefore, T inverse from y to x is also continuous. It's also homeomorphism, but it's continuous is what I want to prove. But remember, but T is already linear, therefore T inverse is also linear. Right? That is automatic. Right? Whenever I have a bijective algebra homomorphism, then F inverse is also the same algebra homomorphism. That is group homomorphism, ring homomorphism, linear map, linear map. Okay, this is what I explained last time in the first session. Therefore, this becomes T, right? Therefore, in some sense, okay, T is an isomorphism of non-linear spaces. What does that mean? So let us look at this. Is not accepted word, but I think of isomorphism as central concept. You may have topological isomorphisms, various names. Okay, suppose x and y are non-linear spaces. I say a map from T x to y is a is an isomorphism, or you want to say topological isomorphism. If first this is a linear isomorphism, okay, this must be bijection and T is linear and T is also homeomorphism. You understand? It should be a linear, bijection and a homeomorphism. Therefore, as vector spaces they are isomorphic, and as topological spaces they are homeomorphic. Okay, that is the kind of isomorphism in the class of non-linear spaces we want to look at. Therefore, this becomes an isomorphism. Okay, please pause. These are the things which usually functional analysis books will not emphasize. Teachers will not say. This is just a theorem. That's it. Okay, why it is called bounded inverse? Therefore, this T inverse is continuous from vertex continuous. That means T inverse is a bounded linear map. That is why it's called bounded inverse. The inverse map is automatically bounded. Okay. So in particular, okay, so again make sure that you understand this, why it's called bounded inverse map. As a corollary, assume the hypothesis as above. Right. Now let's choose a different norm. I'll just write norm x to be norm of Tx. Do you understand this? This is the norm, okay, x with norm. I don't write y with this kind of thing. As I keep saying, my students are all intelligent, so I will not write like this. The context should make clear. So this norm of Tx is this is a vector in y, therefore it's the y norm of this vector in y. I define this. I claim this is a norm on x. That's very easy to check, right? And what we want to claim is this norm is equivalent to the original norm on x. This is for fun. Why? How do I prove? I only have to prove the identity map is continuous. That is identity map from x to this, x to this, and the reverse map, they are continuous. They introduce the same topology is what I have to do. Is that clear? But is this map continuous? Right? Look at that. Okay. Okay. Can I leave it as an exercise for you? So I have x this to y this with the T is continuous, and from here I look at T inverse, okay, that is x to this now. Right? Notice that this is an isometry, because if I have a y in capital Y, norm of y is same of norm of T inverse of x, T inverse of y, because there is an x in x, so that Tx equal to y, therefore the norms are the same. That is norm of T inverse of y. The norm I am talking about is this norm. So this is an isometry. Therefore this is continuous, and composite is what you are looking at. Notice that this is the composite height from x this to x modulus. See, these are the kind of slightly more subtle, involved things. Okay, functional analysis books and textbooks slowly avoid, but it's good to know. If you want to be successful in mathematics and higher level mathematics, this kind of small abstractions also you should be careful. First, make sure this is correct. Okay, because I simply shifted this vectors, right? There is a y, there is an x. Okay, if I have any y here and there is a corresponding x here, okay, what is the norm? The norm of this is look at the norm of this. That's all I'm saying. Therefore, this is essentially the same. Therefore, this is an isometry. You follow that? Okay, and when I say identity, that's a set theoretic map. This map is just a T. This map is certainly T inverse set theoretic map. Their composite identity from x to x. Okay, but this is continuous and this is an isometry. Therefore, the composite is continuous. Therefore, I proved this is continuous. Okay, to master this argument, try to prove this is continuous. Okay, I hope you enjoyed this. Okay, toward the end, try to make it a little more challenging, because my aim is not only to give a kind of exam oriented thing, right? I want you to become a professional mathematician rather than simply pass an exam. I hope you all appreciate it. We will meet again. In the next lecture, we will talk about closed graph theorem. Okay, and stay safe, take care, because there is a next variant, but the variant is no worse than what we already had. So we should be reasonably safe if you have been vaccinated. So be careful. Okay, take care. Bye.